Hello everyone. In this lecture, I will talk about electronic spectroscopy. Now, what is electronic spectroscopy? It is a spectroscopy which is concerned with transition of electron between energy level and covers both the absorption and emission spectroscopies. Now, electronic spectra normally arises because of the transition of electron between the energy level. When transition occurs from lower energy level to higher energy level, it gives absorption spectra, while those from higher to lower energy level, it emit the radiation and it gives rise emission spectra. Here I will talk about briefly both the absorption and emission spectroscopy. However, absorption spectroscopy, there are two parts. One is atomic absorption spectra, which are given by the single atom, which are like sharp line spectra, and another is molecular spectroscopy, electronic spectra of molecular species. Here I will talk about the molecular species only. Now coming to UV's absorption spectroscopy. First, look at this uh, figure. This is the electromagnetic spectrum which comprised of UV range and visible regions. So you can see that this is a region where the 400 to 800, this region correspond to visible region, and before that this is near UV, far UV, and this is vacuum UV. After that, after 800 region, it will fall in the higher range. So this is the UV vis region. Normally the molecules and organic molecule absorbs in the UV region, and where the molecule are extensively conjugated containing chromophoric part, that gives to the higher wavelength falls in the visible region, whereas the inorganic complex where their color, so they absorbs in this visible region. So this is the electromagnetic spectrum containing UV and visible region. Now, what is the fundamental of this UV's absorption spectroscopy? So when a molecule absorbs an appropriate amount of energy, the electron within the molecule, normally the electron which reside in the occupied orbital, is excited to an unoccupied or partially occupied orbital. Generally what happens is that the electron from HOMO, that is highest occupied molecular orbital, transferred its electron to LUMO, that is lowest unoccupied molecular orbital, and this HOMO-LUMO separation gap is such that absorption spectra are usually observed in the UV or visible region of the electromagnetic spectrum. So basically in a molecule there are different energy level. So suppose this is two energy level, one is HOMO, one is LUMO. So electron is paired up in HOMO. So when the when the radiation, when it absorbs the radiation and it excited to the excited state, it may be vacant or partially filled. This amount of energy absorption, when the molecule absorbed, excited to the excited state, and gives this absorption spectroscopy, UV spectroscopy. Now there is one important point to ask. The energies of molecular orbital are quantized, and so an electronic transition is associated with a specific amount of energy change, that is delta E. So this HOMO-LUMO gap, which is given by delta E. So for a molecule, see this delta E, it is a fixed, because the molecular orbital energy is like there is a fixed number of amount of energy is possible for a molecular orbital. So you might expect that therefore the transition from one electronic energy level to another electronic energy level gives rise to sharp spectra, like line-like spectra, just you have observed in the atomic absorption spectroscopy. But in UV spectroscopy, or like molecular spectroscopy, absorption spectroscopy, usually we observe a very broad band. So unlike atoms, molecules undergo vibrational and rotational motion, and these are such that the electronic transition are accompanied by this all the vibration and rotational motion. That is why in the UV spectra we observe very broad spectrum, not a line like spectrum. So, so this is the point to remember, that why UV spectra are very broad in nature. So first point is that this electronic transition is basically a snapshot of the molecule in a particular vibrational and rotational state. So basically this is to electronic energy level. Suppose this is S0, this is S1, but within this electronic energy level there are several such energy level are possible, which consist of vibrational energy level and rotational energy level. Similarly, for excited state also several vibrational energy level and rotational energy level are possible. So when the electron absorbs the appropriate energy, it will goes from S0 to S1. So you may expect there should be one transition, you will get one line like atomic absorption spectroscopy, but here it will carry forward all this transition, that is from vibrational transition also the rotational transition also. That is why there is not a single transition you are getting a bunch of transition which gives this broad spectrum in the UV spectroscopy. So this is the point. So electronic transition associated with simultaneous rotational motion and vibrational transition. As a result, absorption takes place over a range of wavelengths rather than a fixed one. Hence, we got a very broad peak which looks like a typical Gaussian distribution in an absorption versus wavelength plot. Like when you plot a UV spectrum, you will see that absorption versus wavelength, when you plot it, you will see that very broad band. So this is like a Gaussian distribution pattern in the absorption versus wavelength plot, and it will consist of several such transition, including vibrational transition and rotational transition. Now in this slide you can see that there is three absorption spectra are given, but the nature of three spectra are quite different in nature. You can see that the first one, it shows a line like spectra, very sharp line like spectra. So it is for the atom. It is for atom. For atom, we already know that atomic spectroscopy, atomic absorption spectroscopy is it looks like a line, a very sharp line like spectra. Whereas in the for second spectra B, there are several bunch of fine splitting line is there. So it is basically for diatomic molecule. Now this kind of uh, information you are getting because of this vibrational transition between energy level to energy level. But for polyatomic molecule, you are getting a very broad spectra, like which actually comprised of all these vibrational degree of freedom and rotational degree of freedom. As a whole, you are getting a very broad peak. In case of polyatomic molecule, in actually real sense, there are several such transition are possible, are actually occurring, which actually in sum gives rise this broad Gaussian type spectra. So basically, what is the in summary, what we can say that an atom actually does not vibrate. An atom is a single atom, but in a diatomic molecule has the only one vibrational degree of freedom. So that is why you are getting these fine splitting in the spectra, absorption spectra. But for polyatomic molecule, there are several such degree of freedom. You can calculate 3n minus 6 or 3n minus 5, where n is the number of atom in the molecule. So the electronic transition may be accompanied by the many types of vibrational and vibrational excitation, also the de-excitation. So these three following gas phase UV spectra is for one is for atom, the second one is for diatomic molecule, and third one is for polyatomic molecule. So basic difference is that atomic absorption spectra are very sharp in nature because atom does not vibrate. So only electronic energy level you are getting electronic transition, but for diatomic molecule along with electronic energy level you are having this vibrational degree of freedom. In polyatomic molecule there are several such vibrational degree of freedom as well as rotational degree of freedom. Such excitation gives rise a very broad spectrum when you record it. Now let's discuss the important topic, that absorption and Beer-Lambert. Now absorption band in the molecular electronic spectra are often broad, that I have already discussed and may be described in terms of wavelength and the molar extension or absorption coefficient, lambda max. Like you can see that at the right side, top right side, the UV spectra is shown over here. So this is the lambda max, this part is the lambda max, and this is the absorption, or you can plot with the, or you can plot with this molar epsilon coefficient. Epsilon, I'll talk about it later. So how you can plot it with the absorption value or molar extension coefficient with the wavelength or wave number. Now UV spectra, typically normal range is like from 200 to 800 nanometer you can record in a typical UVs in a typical spectrophotometer. Like some higher quality uh, machine you can record up to 1000 plus range, nanometer range, but typical range is like 200 to 800 and among them the 400 to 800 range is the visible range. Now what is Lambert Beer law? So Lambert Beer, from using Lambert Beer law you can actually can calculate the absorption value. So this is very important to understand these two equation and which is given by this Lambert Beard law. I will not going to detail discussion. So this is the absorption value A. So A is given by minus log of capital T. Now this capital T is called transmittance. The transmittance of the sample, and this transmittance of the sample in the solution which is equal to the ratio of the intensity of the transmitted radiation I divided to the uh, incident radiation. So T is equal to I divided by I naught. Now what is I? I is the intensity of the radiation that are transmitted after absorbing the radiation from the amount of radiation transmitted, that is written as I. I0 is the incident radiation. So this is overall the ratio is called transmittance. So minus log of I divided by I naught. So this is, you can calculate by using this formula the absorption of your sample in the solution state. So if the question or if the uh, question ask for the calculation of A value, absorption value, they must given that I and I naught value, or vice versa they can give. So you can calculate this all the parameter. And another part is that absorption A is equal to epsilon into C into L, where epsilon, this epsilon is equal to molar extension coefficient or molar absorption coefficient, C is the concentration, and L is the wavelength and L is the wavelength of that cuvette, that path length of the cuvette that the radiation is actually going past through the solution. Typically for L, normally 1 centimeter. So basically in UV what is happen, what is actually we did actually there. So in the UV cuvette you put your solution, sample solution in the UV cuvette you put the sample in the dissolved solvent, and it is the machine actually detect the absorption value or transmittance value depending on the nature of the machine. So radiation will go. So this is the intensity of the radiation I0, and This is the radiation of the transmitted radiation. This is I. So from this I0 and I value you can calculate the absorption value. Now using these two formula you can understand that the absorption, this absorption actually unit less quantity, dimensionless, there is no dimension. So therefore according to Beard-Lambert law, the absorption is related to the concentration. So basically the absorption is related to the, is like proportional to the concentration of the solution, but the epsilon, that is the molar extinction coefficient, actually it is a property, basically it is a property of the compound and it is independent of the concentration of the solution. Now for like solution concentration of the order of, like if your sample, if your solution concentration see around 10 to the power minus 5 mole per decimeter cube, in that case if you calculate the absorption value actually normally falls within less than 3, this range. Using this formula, absorption is equal to epsilon CL, you can calculate the absorption value. Now in the UV spectrophotometer, this all the system is actually done automatically by the spectrophotometer and the data are the output as an absorption spectrum. The whole range of wavelength is detected simultaneously using a diode array detector, and the double beam setup allows the absorption spectrum of the solvent to be subtracted that from the sample solution. So basically in the UV spectrophotometer, the absorption spectra that you are obtaining, you are getting like this absorption spectra showing in this red color, the spectrophotometer automatically subtracted the absorption that are coming out for the solvent. For example, some compound, inorganic complex or organic molecule you have dissolved in some solvent, chloroform or DCM, and you are getting this spectra, the spectrophotometer automatically subtracted or cancel the solvent absorption spectra. Therefore this absorption spectra is exclusively for your compound, mother molecule, your compound, not from the solvent. Now coming to the types of absorption, how many types of absorption are possible in the molecule which are giving rise to this very broad band. Now electronic transition giving rise to this spectra, absorption spectra, usually fall into following category: sigma star. In the organic molecule, you know there are many such bond, covalent bond, sigma bond. So this sigma star transition. N sigma star, N is the non-bonding orbital to sigma star. Pi star transition, N pi star, non-bonding orbital to anti-bonding orbital electron transfer. Another is charge transfer. This charge transfer phenomena is possible both in case of organic molecule and in case of inorganic metal complex also. And for transition element there is DD electronic transition, which also give rise UV spectra in the visible or UVB region. The energies of most sigma star transition are too high. Because of sigma star energy level, energy difference gap is very high. The wavelength falls very short region, is too short and occurs in the vacuum region. This transition, particularly sigma star transition, because of its high energy, the wavelength falls in the very low number, too short, and it falls in the vacuum region to be observed in a normal UV spectrophotometer. The most intense absorption band normally around 200 to 800 nanometer region, and actually and these all transition, the rest of this N sigma star, pi star, N pi star, all these transition, charge transfer, DD, they actually falls in this region, UV visible region, 200 to 800 nanometer region. Now you look at this UV visible spectrum shown over here. From this UV visible spectrum, you can calculate the molar extinction coefficient epsilon as shown over here. So from Lambert-Beer law, you can rewrite this equation: epsilon is equal to absorption divided by concentration into wavelength, sorry, path length of this of the light that is passed through the solution. So from the usual spectrum, you can calculate the absorption at a particular point. For example, you can see that this is absorption A max, absorption maximum at this point, and corresponding wavelength is lambda max. So particular this position, this lambda max position, you can calculate. You know the what is the absorption value. So you put the absorption value, you know the concentration of the solution and path length of the cuvette, and you will get the epsilon value at lambda max position. So from the usual spectrum also, you can calculate the molar extension coefficient of your sample. And now remember that this lambda max or lambda molar extension coefficient, uh, it does not, it is an intrinsic property of the compound. It does not depend on the concentration. How much you concentrate or dilute the solution, the lambda, the epsilon value will remain constant, same. Now there are certain terminology you need to know in order to understand the visual spectroscopy. One of the term is that red shift or bathochromic shift. So what is red shift or bathochromic shift? So this is the normal, some hypothetical absorption spectra is drawn over here. So if your compound, if the spectra, the wavelength falls right, like falls right hand side to the spectra, when comparing two spectra, we are often interested in whether this band actually shift to higher wavelength or lower wavelength, or higher energy or lower energy. For in a red shift or bathochromic shift, what happens is that the shift of the absorption towards red, like right hand side, higher wavelength, like lower energy, like longer wavelength, lower energy. So basically, red shift meaning is that the transition is giving the lower energy or higher wavelength, that higher wavelength or lower energy. Inverse is true for blue shift. When the transition energy is higher, so basically you are getting lower wavelength, your absorption falls in the lower wavelength side, shorter wavelength side, then this transition is called blue shift or hypsochromic shift. Now there is another two term. One is hyperchromic shift, like if the intensity of the or of your absorption spectra is higher, it calls a hyperchromic shift, or the intensity or absorption is getting down, like absorption is lower than the previous one, it is called hypochromic shift. So basically these two term, some terminology is important to understand. So red shift signifies that higher wavelength, and blue shift signifies that lower wavelength. So this is a very nice example, is given copper 2 complex. You first read the question carefully and then try to solve by your own. This is a copper 2 complex, copper 2, and this is 2 anionic ligand, minus minus. This is phenoxide type moiety which bounded to copper 2, and this amine nitrogen is neutral, and from this NH moiety it is bounded to copper 2. So there is two anionic part and two neutral part and copper 2, and the UV visible spectrum is shown over here. You can see that there is some band. So one is that this is one is on a band around 290 to 92 nanometer. One band is around this this region like 440 nanometer region, and another band is around this broad band around 600 region, and this band actually falls in the UV region. Like the rest of the part falls much lower wavelength, like it falls down in the vacuum UV region. The question says that the UV visible spectrum of a DCM solution containing copper 2 complex, a 1 centimeter cubed. So basically L, the cubed length is given 1 centimeter, was used for measurement. Solution of the complex are brown. So this is a colored complex. The intense band in the spectrum arise from the ligand based pi star transition. You can see that among this transition there is also a solder. So you can clearly understood that among this all transition, this band is most intense band. 292 nanometer band is most intense band, and this band actually arising from the ligand pi star transition. It's given in the question paper. Now the question suggests that how the pi star transition arise. Now you can see that because this 292 nanometer falls in the UV region and it is from the ligand center. Now there is two kind of ligand. One is that this arene moiety is there, bound connected to this phenoxide, this O minus scaffold. Another is this cyclic diamine type moiety, where the neutral amine group is there. Now you can understand this pi star is possible in case of when there is pi bond is there. The arene type, this kind of scaffold, their pi molecular orbital is there, also pi star is there. So this ligand, actually this arene moiety actually causing this transition pi star, giving rise to this band around 292 nanometer, not from this diamine, cyclic diamine. Cyclic diamine don't have this pi molecular orbital and pi star. Therefore this ligand arene moiety giving rise this very intense band at UV region. So you can read the answer also. So pi star transition actually can occur when an electron in the high lying orbital, basically high lying orbital, high energy level, high lying pi orbital is promoted to a low lying orbital. So you can assume it's like from transfer from electron from HOMO to LUMO also, like highest occupied orbital to lowest unoccupied orbital, vacant orbital. So basically high lying pi orbital to low lying vacant pi star orbital. Now the question states that the transition are ligand center. So therefore these pi star transition must be associated with arene ring. The reason I have told categorically why the arene rings are responsible, because this arene ring containing pi star molecular orbital, not the cyclic diamine ring. Now the second part is that which absorption, like one absorption or multiple absorption, give rise to observed color of the complex in the solution. So the question suggests that the solution is brown in color, and there are multiple transitions you can see over the UV spectrum. So you can clearly cut out this 292 nanometer band because it falls in the UV region. So this UV region band cannot give the color of the compound because compound is visible color brown color. So among this transition, this around this transition, this region, you will the transition that are actually occurring, that gives your color. So basically this 450 band actually it is very broad in nature, from 400 to 450 it actually coming, and this around 600 nanometer band, this is actually categorically in the visible region. So basically the visible region band, the absorption band around 6.1 nanometer is in the visible region, and that of 415 is partly in the visible region. So basically this band that around 400 nanometer, this band is partly in the visible region, whereas this band at the higher wavelength band around 600 nanometer, it falls in the visible region. So the third, so this band around 612 nanometer, which is responsible for the coloration of the complex. Now coming to the last part of the question, which suggests that you have to calculate the absorption value. You have to calculate the absorption value of this band, of this wavelength. The 292 nanometer absorption band, you have to calculate the absorption at this region. So this band, this band, so lambda 292 nanometer. So from the spectrum, you know the epsilon value, molar epsilon coefficient value is decimeter cube mole inverse. Centimeter inverse. Concentration is already given 8.8 into 10 to the power minus 5 mole per decimeter cube. Now from Lambert law, if you use the Lambert law, so absorption will come out. You put the value epsilon 10,000 decimeter cube mole inverse centimeter inverse. You put the concentration value 8.8 into 10 to the power minus 5 mole. It will be so basically I have written wrong. So per decimeter, then it will be decimeter cube, and if you just write in this manner, it will be minus decimeter cube, and then CL. L is equal to path length, that is 1 centimeter. So you can cut down all this value, decimeter cube minus mole inverse mole, and centimeter cube centimeter inverse centimeter. So the absorption will come out 0.88. So it is dimension less. So now you understand how you can calculate the absorption value from the visible spectra. So if you know the molar extension coefficient value, you know the concentration, you know the path length, so you can calculate the A. Similarly, any parameter if you need to calculate, you can calculate by rewrite this equation, and you will be given all the other values. Now coming to the second part of electronic spectra, that is emission spectroscopy. I will just briefly introduce the emission spectroscopy. The detail I cannot cover in this single lecture. So first, what is emission spectroscopy? Now you know the energy of the absorbed radiation corresponding to the energy of the transition from ground state to excited state. So basically, molecule absorbs the energy and goes from ground state to excited state. This process you can understand using this Jablonski diagram shown over here. So this is a singlet state S0. This is basically electronic state of the molecule. Ground electronic state, this is S0, and this is this is the singlet state, first excited state S1. So molecule absorb the energy and goes from S0 to S1 state. So basically this transition you are recording in the absorption spectroscopy. Absorption spectroscopy, in the UV part you are recording this absorption part. Molecule absorb the radiation and electron jumps from lower energy level to higher energy level, excited state. But in case of emission spectroscopy, there the process is different. So basically, now this decay of an excited state back to the ground state may take place by a radiative pathway or non-radiative process. The spontaneous emission of radiation from of an electron from the excited state is called luminescence. So this terminology, so what is luminescence? The luminescence basically refers to a spontaneous process, emission process of radiation from excited state, electronically excited state, which covers both fluorescence and phosphorus. I will come to this part. So basically, molecule absorbs the energy and goes from S0 to S1. Then when it returns back, it can returns back in different pathways. So one of the two pathways are fluorescence and phosphorescence, and this fluorescence and phosphorus along they collectively they called luminescence. Now, what is fluorescence? When this molecule comes back from S1 state to S0 state without changing its spin multiplicity, it is called fluorescence. So emission without a change in spin multiplicity is called fluorescence. And phosphorescence, what is phosphorescence? Phosphorescence when molecule changes, when the energy level of the system changes from spin multiplicity changes from, you can see that from triplet state to singlet state, T1 to S0. When this kind of transition is radiative transition is happening, it is called phosphorescence. So fluorescence, phosphorescence, both they are independent property of the molecule. So now this decay of the excited state. So basically this is the excited state. Now this from the excited state, decay can take place in a several possible way. One of these is a radiative decay, that is emission of electromagnetic radiation. So basically these two decay, these are called radiative decay. They actually decay with the emission of radiation, like they with the emission of radiation. They decay with the emission of radiation, nu 1, nu 2. These two, H nu 1, H nu 2, these are radiative decay. And there are non-radiative decay in which the thermal energy is lost. By losing the thermal energy, molecule decays to the lower energy state. Or non-radiative intersystem crossing to a triplet state, T1. So by intersystem crossing also, this electron jumps from singlet to triplet state, is 1 to T1 state. Now we can see that from this, after completing this ISC intersystem crossing, when the electron comes in the T1 state, from the T1 state when it jumps to the S0 state, it gives phosphorescence. However, when the molecule jumps from lower vibrational state of S1 to S0, it gives fluorescence. Now what is the basic difference of these two phenomena, fluorescence and phosphorescence? If you observe the energy difference between fluorescence and phosphorescence, you can see that energy difference of fluorescence is much higher than that of phosphorescence. So basically, if you point out this energy difference delta E1 and it is delta E2, so basically delta E1, that is basically fluorescence, is greater than that of energy difference of phosphorescence. Now what you can tell is that the wavelength of fluorescence will be fall lower wavelength region than that of phosphorescence. Or in terms of frequency, you can say that fluorescence frequency will be higher than that of phosphorescence frequency, because we all know that E is equal to H nu 2 is equal to C by lambda. So energy is proportional to frequency and inversely proportional to wavelength. So basically, in the next example, I will actually, it will be clear out that the wavelength dependent phenomena of this two process, fluorescence and phosphorescence. So all these process, uh, radiative transition, non-radiative transition, they complete with each other. Now emission without a change in multiplicity is called fluorescence. From that S1 to S0, and from T1 to S0, that is change in speed multiplicity, that kind of emission is referred to as phosphorescence. So from the Jablonski diagram we understood what is this kind of transition, how to analyze them, and the red shift, blue shift of this fluorescence phosphorescence as compared to that absorbed radiation. You see, when the molecule absorbs the radiation, it goes from S0 to higher level of S1 state, and when it decay, always the decay energy will be lesser than the absorption energy. So therefore the wavelength of the emission spectrum always will be red shifted. It will be always red shifted as compared to the absorbed radiation. As compared to the absorbed radiation. So from this diagram also, this is the absorption and emission spectrum of a chromium complex with a urea ligand. With the urea ligand, you can see that chromium plastic complex. So you can see that this is the absorption spectra shown in the green line, and this is the phosphorescence, sharp like and broad band in the pink color. This is a fluorescence band. So wave number centimeter inverse, it is along this direction. The higher energy from 12,000, 16,000, 20,000, this wave number region, and this side along this direction you can say this is wavelength. Increasing wavelength in this direction and increasing wave number this opposite direction. So from the Jablonski diagram, what we have understood, you can match, you can actually compare here. What you can see that absorption spectra and these are called emission spectra. So emission spectra are always red shifted, always will fall in the higher wavelength region as compared to the absorption. Absorption will always will be in the higher energy region. You can see that absorption spectra are always in the higher energy region, 16,000, this kind of region. But the emission spectrum will be low energy region or higher wavelength region, red shifted. And comparing the fluorescence and phosphorescence phenomena, you can see that fluorescence and for phosphorescence, so from fluorescence phosphorescence this complex gives both this fluorescence and phosphorescence. So this is a luminescence from a d block metal complex. This is basically luminescence from a d block metal complex, chromium 3 complex with the ligand is urea. In a typical fluorescence experiment, what is actually carried out is that the first absorption spectrum is carried out, is taken, is initially recorded. So when you know the absorption spectra, so this is the lambda max. So this is the basically absorption maxima, lambda max. So you need to know that this lambda max value. So when you irradiate the same sample with corresponding to this lambda max value, when you irradiate the sample corresponding to this lambda max value of the absorption spectra, the molecule will give the emission spectrum, and you record the emission spectra of this chromium complex. Exhibit this kind of both two band, fluorescence band, phosphorescence band, and fluorescence band. And their nature of the band also different. One is sharp, one is broad in this case, and it is recorded. You can see the absorption is recorded at RT 298 Kelvin temperature, but this emission recorded at lower temperature.